Maps. They guide us in new and foreign lands. They remind us that we are mere individuals in the vast space of the world, and they're becoming increasingly ubiquitous as technology becomes more advanced. But what are they, and where do they come from? If you've ever given someone a spherical gift, like a ball, you might have struggled to wrap it in wrapping paper. To get around this problem, you might have just used a gift bag instead of wrapping paper, but your problem would have been nearly identical to the one faced by cartographers since ancient times. How do you represent a spherical object like the Earth on a flat surface like a piece of paper? Unfortunately, this isn't possible. Thanks to the German mathematician Carl Friedrich Gauss, we now know that two surfaces with different Gaussian curvatures are not isometric, even locally. This means that a sphere, which follows a circular curvature pattern, cannot be unwrapped into a plane which has no curvature at all. Some curved shapes, such as cones and cylinders, can be translated from the three-dimensional to the two-dimensional. In fact, the first map of the world, credited to the 6th century BC Greek philosopher Anaximander, was based on a cylindrical Earth. Spherical Earth maps came around 4 centuries later with the mathematician Eratosthenes. Since then, cartographers have proposed thousands of different map projections. None of these is completely accurate, but a few have become extremely popular despite their flaws. One of these bears the name of the Dutch cartographer Gerard Kramer, or more properly Gerardus Mercator. Mercator aimed to preserve angles so that his map could be used in maritime navigation, meaning that this set of equations had to be true. These equations signify that the angles between any two intersecting curves are identical between the Earth and the map, and the curvatures of the curves would have to be altered accordingly. Using sines and cosines to represent the angles of a given point on Earth's surface, Mercator derived the equations for his map. These equations are solved for u and v, which allows us to plug in any location on Earth and find the corresponding location on the map. The constant k allows us to adjust for the scale of the map, and lambda and phi are the longitude and latitude, respectively. Mercator actually derived his map before calculus was even invented, but his projection is just one example of many with strong mathematical roots. Other examples include stereographic projections, which are popular for their accurate depictions of the poles. These projections are obtained by positioning a globe between a light source and a plane, and transferring the illuminated portions directly to the plane. By placing the light source at different distances, cartographers can obtain several kinds of projections. To determine the accuracy of projections, cartographers use Tissot's indicatrix, a system developed by the Frenchman Nicolas Auguste Tissot. Tissot's indicatrix is a series of ellipses marked on a map that reflect evenly spaced points on the surface of the Earth. In regions where the ellipses are circles, the map in question preserves angles, and in regions where the ellipses have a constant area, the map preserves area. In summary, even if we can't create a perfect map, we can create maps that preserve at least one of the fundamental elements of cartography: angles, length, and area. In order to do so, we can use mathematical models of shape and size that help us translate from 3 dimensions into 2. So, the next time you use a map, physical or digital, to find your way around an unfamiliar place, take a moment to contemplate the mathematical beauty and impossibility of the world we live in.